Today we're going to talk a little bit about the photoelectric effect. Now, it is well known that Albert Einstein won the Nobel Prize in Physics in 1921 for the photoelectric effect and, more importantly, the interpretation of the photoelectric effect. This is where the term photon, that is widely used when talking about light, comes from. So the photoelectric effect is almost exactly the same as the Compton scattering. They both have incoming light rays striking electrons, and they both have electrons being moved and transported in some other direction. And so you can see that here and you can see that here. The main difference between Compton scattering and the photoelectric effect is in Compton scattering, the electrons are not bound to any material. In the photoelectric effect, the electrons are bound to a metal. But before I go on to talk more about the photoelectric effect, I want to point something out here. Now, these two images I got actually from Wikipedia. And the problem I have is that in this Compton scattering depiction, you have something that looks like a light wave. This is actually how they commonly depict photons. They often depict it as a pulse, more like this, so like an impulse. And so they often depict the photon as an impulse. And so here is a depiction of Compton scattering where they have a incoming photon that looks more squished and an outgoing photon that looks more stretched out. And that makes more sense to me in terms of what I know about the Compton scattering. And so, but in this image here from Wikipedia, it looks like they have a wider photon going in and a smaller photon coming out. And so I find this very confusing. Here is another depiction where you have the incoming photon looking kind of like this, where it starts out small and goes bigger and then goes small again, like an impulse. I think they refer to this as an impulse. And then the photon that's coming out is more stretched out. Okay, so I think there is a lot of confusion, even in the mainstream, as to what is a photon and how to draw a photon, how to depict a photon. And so, but this is what Wikipedia is doing. They are showing this as the incoming wave and this as the outgoing wave. And this doesn't really match what other people are doing, because it looks like the outgoing wave is smaller than, less stretched out than the incoming wave. And in these other depictions, you have this impulse, this this impulse here looking more stretched out than the incident photon. And so this is why I don't really like the concept of the photon. I don't actually think mainstream really understands the photon very well. They think they know what the photon is, but when they're depicting it different depending on who's doing the art or whatever, I don't know. There doesn't seem to be a consistent rendering of of what a photon looks like. And so I prefer this kind of drawing here where the incident photon, but I don't call them photons, the incident waves look like a wave and the outgoing wave looks like a wave. And so I prefer this kind of depiction of both the Compton scattering and the photoelectric effect, where the incoming light, which aren't photons according to my language, they're just waves. Wave fronts really are coming in, and wave fronts are going out at with a longer time between wave fronts. And so you have a wiggly thing coming in here, you have a wiggly thing coming in here. That doesn't look like an impulse. And so this depiction matches more the language that I'm promoting, where light is a wave coming in and light is a wave going out. Light is a wave coming in that's knocking the electrons off the metal, resonating it off the metal, and the electrons go flying off at a velocity. Okay. So what is the difference between this and this? As I said earlier, the photoelectric effect is almost exactly the same as Compton scattering. The only difference is the electron in the Compton scattering experiments are not bound to any material, and the electrons in the photoelectric effect are bound into a material. So they are bound into the metal, and in order to make an electron move, so in this experiment, in order to make an electron move, the incident light can be any frequency, and it will scatter off of an electron. And so it will bump into an electron and move the electron, even if it is a very low frequency. If it's a very low frequency, the velocity is going to be very, very slow. And so in the photoelectric effect, the only difference between these two is that the light that's coming in first has to break the binding energy of the electron to the metal, and then any excess energy that it transfers to the electron will be converted into velocity. Okay, so that is the only difference between the photoelectric effect and Compton scattering, is that you need to put in more energy. The energy that comes in has to be greater than the binding energy of the electron to the metal before it can scatter the electron, before it can do this. It has to first break the binding energy of the metal or the electron to the metal. So this is really not that difficult. It's not that difficult, and yet Albert Einstein got a Nobel Prize in physics for the photoelectric effect. Okay, photoelectric effect is very useful, and maybe that's why he got the Nobel Prize for it. But the photoelectric effect is really no different than Compton scattering, which I believe they already knew about at the time. Maybe not, I don't know, but I think they did. And so what Albert Einstein really got the Nobel Prize for, I believe, is the creating the idea of the photon. And so I'm going to talk more about the photoelectric effect and go into more detail and crunch some numbers for you in a future video. But, you know, what I want to do for the rest of this video is I want to try to explain why I don't think that the photon actually exists, that light exists, and light does strike electrons, and it does transfer momentum to the electron. It does knock electrons off of a metal, but the reasons why it does it can be explained differently using the language that I am developing and promoting. Truthfully, I think Albert Einstein was given a bad deal. I think he had a poor starting point in terms of unit analysis. I think he because something was missing from unit analysis, he made a mistake. Okay, so I believe he made a mistake, and the mistake starts here. So I'm going to explain this mistake kind of backwards from the way I usually do it. And so as you saw in my previous videos, I model Planck's energy equation as a power equation. So I call it Fractal Woman's Power Equation. No, I'm just kidding. I don't really want to name things after people. You know, I don't like doing that. And so when I call it Fractal Woman's Power Equation, I'm just doing it a little bit tongue-in-cheek. And so the power equation from the language I am developing looks like exactly like Planck's energy equation, only it's written in terms of power. So in this equation, power has units joules per second, and Planck's constant has units joule per cycle, and frequency has units cycles per second. So what I'm claiming is in this equation and in the original energy equation that there is a missing time variable. Okay, there's a missing time variable in these equations, and so what I'm going to do is I'm going to put the time variable back into the equation. So the first step is to write power the power part of this equation as energy over time, because power is energy over time, energy per time. And so I'm going to write this equation as energy over time, only I am going to set t equal to 1. Just for now, I'm going to set t equal to 1. And so energy over time, but t is still a variable. T is a variable. T can be anything. And so, but for now, I'm just going to, in my mind, I'm going to set it equal to 1. So now energy over time has units joules per second. Power has units joules per second. But now E has a unit and T has a unit. So now both of these units have a corresponding member in the body of the equation. H has units J joule per cycle. Frequency has units cycles per second. Okay, so I just put this missing time variable back in the equation where it belongs. So next, I am going to multiply both sides by t. Okay, so I am going to write this equation now, instead of being a power equation, this has now become an energy equation. And so we have energy is equal to Planck's constant times the frequency of light times some time variable times this measure time variable. And again, I, in my mind, set t equal to 1. So here's what happens when I do that. So here, this time variable belonged to this unit of time here. So this unit of time here had a home right in this time variable here, and then I multiplied both sides by s, by the second, by the time variable, and put the second over here. So you can see what I did was I took this s and put it over here, and I put this t and put it over here. And so now we have this equation here where energy has units of joule, Planck's constant has units of joule per cycle, frequency has unit cycles per second, and time, measure time, has units of second. So now every term in the equation, not now, but every term in the equation has a unit associated with it, including this time variable. So notice I said time variable. Okay, this is a time variable. This is the equation of an experiment. Okay, in the experiment, you're collecting energy units, and you're doing it over some time interval. And so, so here's what happens. So if you set time equal to 1, you don't have to, but when you set time equal to 1, that happens. And so I believe what happened in the past is whoever wrote this equation didn't take into consideration that there was a time variable in this equation. This is the equation of an experiment. And so when you set t equal to 1, but you don't know, you don't even know there's a time variable, then this happens. The time variable disappears. And so now we have this extra unit of time. We have this extra unit of time that kind of has nowhere to go. Okay. So the only thing you really can do is this. So without the time variable, which is here, okay, without the time variable in the equation, this extra unit of second, the extra unit of time, has to go here, or it has to go somewhere up here. And so, and also the mainstream language doesn't have the delta term. They don't have the cycle term. And so that is how the units of Planck's constant came to be joule times second, in my opinion. So it's my opinion that this equation, Planck's energy equation, is the equation of an experiment in reality, and should be written like this. And so what if the experiment is 10 seconds long? As I said before, t is a variable. It's not a constant. It's not meant to be set equal to 1. But if you do set equal to 1, then you end up with the original equation. And so what if t equals 10? Can we set t equal to 10? Well, of course we can. T is a variable. And so I'm going to write this. So the way this reads is the energy of a 10-second experiment is equal to Planck's constant times the frequency of light, which is on a per second basis. So the energy of light is always reported as hertz, as cycles per second, not per half a second, not per 2 seconds, not per 10 seconds, but frequency is always reported as cycles per second. So this term here is on a per second basis. And so then you have to multiply the experiment by 10. So the total energy of a 10-second experiment is equal to Planck's constant times the frequency of light times 10 seconds. Times 10 seconds. And so if you want the energy in terms of 1 second, you divide both sides by 10. So this seems fairly straightforward to me. This seems actually very obvious to me now that I'm saying it. But if, okay, so now what if t equals to 1? Let's set t back into 1. So now we have energy equals Planck's constant times frequency times the variable t, which we just set to 1. Okay, so then you get the energy of 1 second is equal to Planck's constant times the frequency of light times 1, obviously. And that gets us back to the original equation, because t is equal to 1. And everyone knows that when you multiply something by 1, you get back the thing. But is it the right thing to do? Is it right to take, even though we set t equal to 1, is it right to write this like this? And I say, of course, it is correct to write it like this, as long as you know that this equation is on a 1 second, in terms of 1 second. Now, it seems like the mainstream language has a little bit of a problem with this numerical value of 1. They have a strange relationship with this numerical value of 1. So as I showed you before, it looks like the language, they inadvertently injected the numerical value of 1 into the unit section of this equation. And then they used it as the numerical value of 1, multiplied that by joule to get the result that they wanted. Of course, the units had to work out to be the joule, and this is how they did it. Regardless, this seems like a big mess to me. It took me a long time to unwire myself from this mess and to try to figure out a better way of explaining light without invoking the action constant and without invoking the concept of a photon, which, as we saw earlier, I think is grossly misunderstood. So where does this leave the photon? Obviously, Albert Einstein got the Nobel Prize for basically discovering the photon. But as I showed you in my previous videos, I can rewrite this equation in terms of power, and I can solve problems by using the power equation and the companion force equation, which looks exactly the same, only it is force is equal to h over c times frequency. Okay. So I can solve all the problems using the power equation, and as you can see when you look at the units, there is no action constant. There is no action constant, and obviously power is on a per second basis. So I am interpreting this equation as the unamplified power of light that is emitted or that is created by an atom, however that is done, whether it is a perturbation of the medium or whether it is a some other way of creating this wave. Light is a wave that has a power that we can measure on a per second basis. And when you have an amplified power, such as laser, what you do is you take the amplified power of the laser, divide it by the power that you calculate here based on the frequency of the equation, and you get the amplification factor of the laser. And so when you interpret this equation in terms of power, we don't need the action constant, and we don't need the concept of a photon. The photon, this is the equation of the power of 1 second's worth of wave fronts. Okay, wave fronts. This is the equation of the power of 1 second's worth of wave fronts. And when you amplify the signal, as you would do with a laser or with a radio signal, then you would divide the power that you calculate, the amplified power, by this power, and you get the amplification factor. So that is how I am converting the standard language to my language, to the own particle language, to modified unit analysis. And in my language, if my language turns out to be correct, then Albert Einstein made a mistake. Okay, he made a mistake, but the mistake was in interpretation. The physics is fine. The numbers are fine. Everything works out fine. The only thing that was a mistake was the interpretation. And this interpretation was based on a flawed unit analysis. Okay, so that's my piece for today, and hopefully I will be back soon.